Welcome back to Class 9 in Thermodynamics. We're moving on to Section 3.6 in our textbook, where we talk about heat transfer modes and the rate of heat. So when we talk about heat, we're moving from one state to another state, and it's really the heat transfer is what Q is really talking about. And sometimes the rate of heat transfer, that Q dot, is one of our goals. So if I had mentioned at the end of the last video that you will take, if you're a mechanical engineer, an entire course called heat transfer. So a lot of the things we're talking about lay down the groundwork and maybe are things that get covered in a lot more detail. So here we go. Let's take a look at the different kinds of heat transfer modes. The first one, let's see if I can get this, there you go, is conduction. And conduction right here is when we have direct contact between two things. So this handle right here is going to transfer heat right into the hand because they're touching each other. And it's that direct contact that defines that conduction. Convection, however, as you're seeing right here, it requires like a medium to be moving, right? So it's the moving fluid that's causing the heat transfer. So you might have a solid surface somewhere in here, but it's the liquid that's touching that solid surface, and maybe the boiling of this water turning into little steam bubbles, and the movement of it. It transfers that heat from the solid surface into a fluid and is moving around. And fluids touching fluids can also be convection. You could have steam. It is touching the air, and even the active evaporation right here. Those are all means of this convection. And it's a fairly complicated heat exchange mode, but one of the very most common ones. Radiation doesn't require, the medium by which it goes through will not influence. So it could be in a vacuum, or it could be in air, it could be, well, I guess it could be in water, but most of the time we're talking about a gas that's going through. And so it's moving. So you can think the sun radiation, or from a light bulb, or in this case, the heat right here, because we're not in direct contact, it's being lifted off right there. But it's hot enough that to keep heating that thing up. So it's transmitted through electromagnetic waves. And then there's a combination. Well, in most practice, there's quite a few things going on in heat transfer. And of course, you'll be taking an entire class in this. We usually quite often will assemble, we will assemble sort of like a type of heat overall coefficient to kind of describe how this moves. But regardless, it's always the difference in temperature that is driving this heat rate. So here's some more information, some more words to look through. So we have the exchange by direct contact for conduction. And it's found by what's called Fourier's law of conduction right here. I can't remember what this negative sign connotates right there, but I think they're trying to convey something to you. Most of the time I've dealt with this, I haven't dealt with a negative. But you have this K, it's called is an empirical constant that's put together between, some things can conduct heat a lot better than others. A is the surface area perpendicular to the direction of the heat transfer, right? So if we went back up to that hand, it would be how much surface area the hand is touching the handle. And dx is an incremental distance, right? So it's a lot of this could be, when we're doing a simple problem, this could be the thickness by which that the thing is moving through. And of course, then there's the temperature difference. And so this is, as you're going through maybe something that's thick, the temperature might be changing and with position as you're going through. So that's one of the reasons why we put up here. Quite often we will simplify this by just the temperature difference between each side of the thickness of the part, and that'll be what that turns into. Convection, now this is much more complicated because there's lots of factors going on. So like you could say the wind that's blowing along, or maybe if you are standing outside and the wind is blowing, amongst the things that are taking place is that because of the wind, the higher the wind, the more heat is being transferred, right? So the velocity, it plays a part. There's also something called a boundary layer, and the thickness of the boundary layer, that's also related to like maybe the fluid mechanics of what's taking place. Um, so when air is flowing over like a radiator, maybe, and water is also flowing on the inside. So it's a little more complicated in that because we have two separate like events taking place, if you can imagine. So like maybe if you're inside a radiator, we have like a tube. So here's the tube right there, and through this tube right here, that's going to be conduction that's taking place. But over on this side, maybe we have like air blowing across here, and over on this side, and this is just like I'll try to just draw like air or whatever. It's not a coil. I'm sorry. I'm just trying to draw like wind. Or here's like water flowing past onto the side. So in between, I'm not sure if I'm doing a very good job of explaining this, but in between here is like a boundary that's going to take place, and there's going to be heat that gets transferred through there, and that's going to be the convection. But then over here is going to be the conduction as it goes through the thickness of the wall of the pipe, and then out the other side, it's going to have another convection that's going to take place right there. And then I just screwed up all of my things. I said, let's erase all that. So here's the equation. Do we give it a name? I think this is actually called, I should have written it down. This is actually called Newton's law of cooling. So write that down somewhere. Newton's law of cooling. Maybe I'll write it. No, I'm going to go laser pointer, apparently. Doing a great job. Now I got the highlighter. You son of a gun. All right, so this right in here, Newton's law of cooling. And we have the area, the surface area that's exposed. All right, so I kind of went in the other direction as them. All right, so we have, I lost my pen. Where'd it go? There you go. We have the area, surface area, over which heat is transferred. So if this was your skin on a cold day, that would be how much surface area of skin that you have. We have this overall heat transfer coefficient, which is complicated. It depends on what the media is. I mean, is it air? Is it water? Is it air-water mix? The flow velocity, but also whether it's laminar or turbulent, that's going to play a part, and then also the geometry. So H isn't a very easy thing to just pull out of a book for many different situations. That's why you take an entire course in heat transfer. And then you also have the temperature difference, right? And so some of these things require a pretty good amount of assumptions and estimations in order to be practical. And you're not going to get a really, really accurate answer except through experiments usually. Radiation, remember that's electromagnetic waves, that happens in space and doesn't require any matter. And quite frankly, it's not really going to be affected by the matter. What it really responds to is something like that's dark, right? Something like they call it sometimes a black body. Something like, so if you wore a black shirt out in the sun, it would be absorbing some of the radiant heat more than if you wore a white shirt. So we have several things in this equation that will be noted. We have this epsilon, which is emissivity, which is like the fraction of a black body, right? So I think 1 is something that would be black, and then maybe close to 0 would be something that was like highly reflective. We have this sigma, which is the Stefan Boltzmann constant, right? So that's nice to have a little constant that you can look up. A is the exposed surface, and then TS is the surface temperature. And quite often what we'll do is we will have, we'll actually go this right here, and we'll have like that right there. So we will be moving from one body to another. So whatever we started out with right here, and then here's what we're going to end up with for the surface temperature. But so anyway, that's like the idea for these three modes of heat transfer. We also just notice that we usually in practice we're going to use some type of simplification, and we actually kind of use it like a conductivity or like inverse of the resistance, and we assemble a total resistance based on the scenario that we have, most often from conduction and convection, but it could have some radiation. All three of these modes might be being put together. So we have like this kind of like resistance that we like assemble together. We're not really going to do that in this class, but just be aware that this does happen, and commonly. So the next videos will be a series of examples, I believe. Well, no, we'll do an example and then we'll do internal energy. So I got that to look forward to. That's great.